Okay, so the last class we were looking at linear systems, linear guidance systems, specifically with respect to what you call path following. So we are trying to generate the paths which can then be used for our craft to follow. So we were looking at waypoint approach. So the most of the times you will see that the path is specified in terms of discrete waypoints, and typically you try to follow either a straight line path or sometimes a curved path through the waypoints. So far, whatever we have discussed more or less looks at straight lines through the waypoints, except the inscribed circle path method. That is where we were looking at the idea that when we have the multiple waypoints, the path is actually planned in such a manner that a part of the path actually passes through a circle inscribed on the two sides of the three waypoints. And we understood the idea that there the problem is that you actually don't go through the waypoints. So in such an approach, you are only using those waypoints to guide the path, but precisely you're not going through the waypoint. Then we looked at a new idea, the straight line paths based on circles of acceptance. And we prescribed this as an alternative to the inscribed circles method. The idea here is that you have to be within a certain radius of the waypoint in order for that waypoint to be provided to you as the tracking waypoint. Or the other approach is, after I have come within a circle of acceptance of one waypoint, I am given the next waypoint as the next target to track. And we understood that there might be certain issues in such a scenario, that when I don't actually fall inside the circle of acceptance, there's a potential chance of me never being provided with the next waypoint. And that is where we discussed that this switching can be done in a slightly different way. And that is where we looked at this idea that we are looking at what you call along track error, and using that as the concept to decide when to provide the next waypoint. So here the idea is that when the along track error is equal to the distance between the waypoints or within some region of the distance between the waypoints, I will choose my next waypoint and ask it to start tracking. And I said that yes, this is more robust than the circle of acceptance method, but nevertheless, it still fails if my ship is headed in the opposite direction, like I see here, right? In which case, you'll never be able to reach you'll never be assigned the next waypoint. So there is a pinch of salt to take it with. So sometimes you may have to program some other logics in order to make sure that this guidance methodology works seamlessly on your applications. Okay, this is where we discuss some of the mathematics of it. Yes.
In the above picture, like that along track errors, if we are calling it an error, like when it reaches that xi plus 1, y plus 1, it should be 0, right?
No. So it's not technically called an error. Here, the conception is that since we call the cross-track error, the name has stuck around with it, but it's not really an error. It's how much distance you have proceeded in the along track side.
Okay.
So when the along track distance is equal to the distance between the waypoints, then you would have at least reached horizontally in the same direction as your next waypoint. So it's not an error per se, but because of the cross-track error being defined in that manner, the name has stuck around, but actually it's not an error. It's distance, how much you have moved along the line connecting the two waypoints. That's what it represents, essentially.
Okay, sir.
Okay, all right. Okay, so today we are going to discuss a little bit about Dubin's path. We'll not be going into the theoretical details of how to generate a Dubin's path and all. We'll more or less stick to the conventional idea of what a Dubin's path is and how it works, but we really will not go into the implementation. Possibly I might include something on this in the assignments, in the future assignments, so as to take a look as to how to generate these paths. for our guidance purposes. The idea here is that if I choose any two orientations, so if I'm given xi, yi, and psi I as the initial orientation, and xi plus 1, yi plus 1, and psi I plus 1 as the next orientation. So if I call these two poses, okay? So pose being that it is not just specifying the position, but is also providing the orientation along with it. Then the shortest path which connects these two orientations for a craft that is moving at a constant speed u, it can be shown mathematically that such a path would be formed by straight lines and circular arc segments. Okay, now we are not going to look at the so-called proof of this statement. This is a statement which has come from Dubin in 1957, and later on it was proved much later, probably decades later. They found the proof that yes, indeed, this leads to the shortest path. But for our purposes, it suffices to know that a shortest path between two poses for a craft moving at a constant forward speed is a path formed by straight lines and circular arcs. Later on, even further simplifications were performed, and they said that the optimal path generally will be listed from these 6 possible optimal path configurations. And what are these 6 configurations? They are representing, each of the letters here is representing either a right turn or a left turn or a straight line. So the right turn is denoted by R, left turn by L, and straight line by S. So an optimal path that connects to any two generic poses would be involving a right turn, a straight line, and a right turn, or a right turn followed by a straight line followed by a left turn, or left straight right, left straight left, right left right, and left right left. So you'll see that the first 4 components generally includes a straight line component as a part of it, and the last 2 include pure turning way to reach the waypoint, the next pose waypoint, which I am specifying. So here what we are assuming is, notice that when we specify the right turn and the left turn, we are assuming that there is a bound on the turning rate. So I can't turn as quickly as I want, but there is some limiting factor of how fast I can turn. Or you can even specify this in how sharp your radius of curvature can be. So in either cases, that constraint is taken into account when you are formulating the path between the 2 orientations which are specified. So let's take a look at one example. So let's say that I am at this location and my craft is oriented in this direction. Okay, I want to go to this position with an orientation which looks like this. Is everybody with me? Yes? No?
Yes, sir.
Okay. Now the idea is that I'll first form a radius of the sharpest turning radius that I can form around this path. Okay, so this path will be the tangent to that circle which I form. Similarly, I'll also form a circle where the final orientation is a tangent to that circle. Is everybody following me now so far? Please tell yes or no, because I am not able to see you guys.
No.
Yes?
Yes, sir.
Okay. All right. And then what I am saying is I'll connect a straight line which will be a tangent to both the circles. And my path will basically start from my starting orientation, go along the first circle until it reaches this common tangent, then follow along the straight line, and then continue my path over the second circle. Okay, that is the idea. Similarly, if I had any other configuration, I'll still do the same. Now, when it comes to the last 3, the same process applies here, that instead of finding a common tangent between the 2 circles, I'll find another circle which is tangential to both these circles. So my path on the first circle will continue until that tangent point. Then it will continue on to the second circle and then come back to the third circle. So it will look something like this maybe. So I might have a circle which is tangential to both. So suppose I'm starting at this orientation and I want to end up with this orientation. Okay. So then I'll follow along on this path here and then probably follow along on this path here. Okay. And then, okay, I think I messed up here. Okay. So imagine that if the final pose is this way, I probably want to form the circle this way. Maybe not. 1 second. Let me see where I messed up. So if I have my orientation in this manner, it is pretty clear that I'll go this way, right? I'll make a right turn first and then make a left turn and then come back and make a right turn and I reach the orientation that I want to reach. Okay. But if I have the orientation were reversed. Okay, if I wanted to reach this point, then I can't use the circles method to get there.
So we can form the circle like to the goal state. We will form circle that is tangential, and we will extend this line. Like first circle we will leave up. We need only one circle.
No, sorry, come again.
You are done 3 circles, right?
Mm-hmm.
If we make only one circle, which is like a bigger circle maybe in between these.
In between these two circles.
Yeah, instead of this bigger circle, opposite side one bigger circle.
So you mean like this?
Something similar, yeah.
Yeah, but that was not giving me. That was the problem. I go this way, and then I. Okay. So if I change the color here, just to see. Yeah. So I go this way, but then I can never reach that orientation. I have to follow along in this way, but I can never reach that orientation. The only way that I can do this is if I have the first circle here, with this being the path, and the other orientation is this way, I form the circle like that. Okay, so that too may be difficult. Sometimes not all 6 may be possible. That is also there. Okay, not all 6 may possible for all orientations. So sometimes, so suppose this initial orientation was here, then I possibly could maybe make a tangential path here, follow along this way, and then come back this way. That's a possible way. But suppose my initial orientation was not there, but my initial orientation was, let's say, somewhere here. Then too maybe I can do that. Yeah, so in this case it is possible. But if I put the circle the other way, which is what we saw here, right, in the other case, in which case I can't do I can't use 3 rotations to reach there. No matter how I take the 3 rotations, I can't find a path from first orientation to the last orientation. Okay. In this case, or the other approach might be that I have to settle for a straight line in between. So the point being is that whenever we are using Dubin's path, these are the 6 possible. So your optimal path between which connects these 2 waypoints will be a part of these 6. So one of the 6 will be the optimal. That is what Dubin's path basically tells you. It doesn't say that all 6 will necessarily exist. Some of them may not exist for a given configuration. So whenever you are provided with 2 orientations, which you want to go from one orientation to the other, you can try to evaluate all the 6 of these paths, figure out which of the path has the least path, okay? And then that will be your shortest path to the goal location. So Dubin doesn't say that one specific one only will be optimal for one position. He says that all 6 will be a possible choices. Some of them may not exist, but you must want to find out all the 6 ones, figure out which one is the lowest path, choose that as the optimal path and move forward. Okay, so that is the primary idea behind it. Now I'm not really going into the math of it in this because now it's starting to become a more geometrical problem. But at least you get the idea of how to connect 2 poses from one pose to the other in such a manner that your speed is not changing. So you're maintaining the same speed, but you're trying to find the shortest path between 2 orientations. Okay. Now, later on, people have also shown that this can be extended to include obstacle avoidance. So they have done that. So there is one paper here from 2010 which discusses that. Similarly, what happens in the presence of ocean currents and uncertainties which are present, how do you deal with them and how well is the performance of Dubin's path in such a case has also been discussed sometime in 2006 to 2010. So a lot of work you'll see has happened actually sometime in the late 90s and the early 2000s in this area. Okay, so primary idea, so to summarize the Dubin's path, to connect 2 orientations, we will usually look at the 6 possible combinations to connect the paths. And once we have a few of them, so some of them may be possible, some of them may not be possible. So whichever ones are possible, you will evaluate what is the path length for each of them, and whichever one is the least, that becomes your optimal path connecting the 2 orientations. Okay. Okay, so that was a very brief description about the Dubin's path. For most purposes, for now, we'll come back to talk about the straight line path following, and let's look at if we wanted to apply this straight line path following in guidance system and provide it to a control system, how do we go about it? So this picture we have seen before. It is the same picture as before, but I've recreated it here in order to discuss it. Okay, so we have the NAD frame where this xn denotes the north direction, and we have the first waypoint, the initial waypoint, as xi, yi, and the goal waypoint, which is xi plus 1, yi plus 1. Now we define a path tangential system such that the x-axis of that path tangential system, denoted by xp, is directed from the initial waypoint to the next waypoint. And obviously, y will be governed by the right-hand rule. Since z is pointing down, you can see that y should point in this direction that's shown here. Okay. Now, let's assume that at any point at a current time, the location of the craft is xn, yn. Okay. Notice that whenever I'm putting this superscript n, what I mean is that I'm calling these quantities in the NED frame. Okay. In the northeast down frame is where I'm referring them to. And it has a velocity vector which is pointed in this direction called u. And we are looking at what is the angle between the north direction and this velocity vector. That is our course angle. Okay, that is our course angle. Correct. Similarly, we can define the course angle with respect to the path tangential system, which we call as chi p. Now that is the distance or the angle from the x-axis of the path tangential frame to the velocity direction. Okay, is everybody seeing this? Same idea, only that the path tangential system's x-axis is pointed in a different direction. So we are looking in that direction. Notice that here, both of these cases, the positive convention will always be governed by the right hand thumb rule with thumb pointing in the z direction. So since the z is pointing down, I'll see that the clockwise direction is what is taken as the positive direction. Is everybody with me so far?
Yes, sir.
Okay. All right. Now, with respect to this position, I can now define the cross-track error, which we call it as YPE, and the corresponding x coordinate, which we call it as XPE. Now, XPE is the distance that I have moved, or the distance the craft has moved along the line connecting the waypoints, and cross-track error is how much it has deviated from that line in the perpendicular distance. We saw that this YPE dot, okay, so the so-called derivative of that YPE is nothing but u times sine of XP. So I'm taking my velocity vector, pointing it in the perpendicular direction to this line connecting the waypoints, and that is the velocity with which the craft is moving towards the line. So therefore YPE dot is given by that. Is that making sense? Yes, no? Everybody clear on this? If not, tell me, we'll explain again, no issues. Just imagine, let's say that the craft is oriented the same way, but the velocity is pointed this way, let's say. Okay? So then the line connecting the two waypoints, if I draw that parallel line here, then this is the angle, correct? Which will be psi p. Yes? U times sine of chi p will be the velocity which is pointing in this direction. Correct? And that will directly impact my YE dot. That is the rate of change of my YPE. Okay. The confusion might be coming because the craft is oriented in such a manner, or the velocity vector is oriented such that this XP is an obtuse angle, which might be causing some trouble in understanding how that is coming about. But if we just change the velocity vector to a different direction to observe what is going on, it will be pretty clear that U times sine of chi p is nothing but YPE dot. Is that making sense for everyone now?
Yes, sir.
Okay. All right, good. All right, now if this chi p is a relatively small angle, okay, assuming that this is a small for straight line path following, so assuming that our craft is not deviating much, then I can say that YPE dot is almost equivalent to U times chi p. Okay, because sine of a small angle will be almost equal to the same angle as long as the angle is not too large. I'm not looking at very large deviations here. Now, it is easy to see that chi and chi p are basically related by this expression. Chi is equal to pi p plus chi p. So what am I doing here? I'm saying that chi is equal to pi p plus chi p. Okay, one second. Let me write this down a little better. All right. Is that making sense?
Yes, sir. Yeah.
So if I take the craft, let's say I erase everything here and make sure this is clear enough. So instead of the velocity vector pointing that way, I take the velocity vector as before, pointing this way. Okay, so that is my u vector. Then we know that this angle is chi, correct? And if I draw a line parallel to that line joining the two waypoints, then this angle is pi p. And since the x-axis is pointed in this direction, this angle is chi p. So pi p plus chi p is chi. Is that making sense?
Yes, sir.
Right.
Yes, sir.
Okay, all right. Now, let's say that we assume a so-called Nomoto model for our yaw dynamics. I know that we did not really cover this Nomoto model in our course, but most of you have seen this before, either when you have taken maneuvering, and most of you have seen this when you took the maneuvering course, that we can approximate the yaw dynamics by a single degree of freedom system, and the single degree of freedom system's linear differential equation which governs the yaw rate is given by T times R dot plus R is equal to K delta, where R represents the yaw rate, delta represents the rudder angle, T represents the so-called Nomoto's time constant, and K represents the Nomoto gain. And this is the differential equation which will govern the yaw dynamics or a slowly moving ship. So taking a Laplace transform of this, we will get R of S is equal to K divided by Ts plus 1 times delta of S. Okay, everybody comfortable with this so far?
Yes, sir.
Okay. All right. Now, if we consider that in addition to this yaw dynamics, which is purely representing the hydrodynamic phenomenon, there is an additional disturbance which is coming in, which I will call as dr. Okay, then that dr basically is capturing the influence of, let's say, ocean currents, wave drift, and wind. So I don't know what the dr is, but I'm just including it, saying that these are the effects, let's say, coming due to external factors which are not in my control. Okay, due to the environment's effect, we are seeing this coming. In which case, now I can take my new transfer function for R as the previous one plus this delta R. Sorry, not delta R, this is dr, okay, disturbance which is coming in R. I can integrate this to get the value of psi. So I can see that this will become K divided by S times Ts plus 1 times delta plus dr by S. Everybody understanding so far what's going on?
Yes, sir.
Anand, you're able to follow me?
The last step, I don't know how it got converted.
Okay, so we know that psi dot is R, right? We know that the rate of change of yaw rate, R is nothing but yaw rate, right?
Yes, sir.
So if I take a Laplace transform of this, what do I get? Yes? Is this making sense?
Yes, sir.
Okay, so therefore psi is nothing but R by S. So simply I take this entire thing and divide by S.
Yes, sir.
So that's what I'm seeing here, right? Okay, now I know that the course angle chi is nothing but this heading angle psi plus the crab angle beta c, and this is from a way back in the lectures which we had discussed, where this thing was basically tan inverse of v by u. Okay, where it is basically representing the so-called drift of the ship, how much it has drifted. So the difference between the velocity vector pointing to the heading angle, that difference is what is the drift angle usually, right? Here, if the velocity is pointing in the longitudinal direction of the ship, the drift will be 0. But as long as that's not the case, you'll see a drift angle, and that is why you have this relationship that the course angle is the heading angle plus that so-called drift angle. Everybody with me so far?
Yes, sir.
All right. So now I can substitute my psi into here. So I can get the expression for course angle as k by s times ts plus 1 times delta, plus I have some extra terms. I have the beta c and I have this term. I combine them both together to call it a disturbance in chi. Okay. So I call that a disturbance in chi. Now, why am I going through all this effort? I'm trying to put everything together in terms of the so-called the cross-track error. So now that I have the course angle, I now know. See, we started all of this with the idea that ype dot is equal to u times chi p. Okay, so which is nothing but u times chi minus pi p. So if I know the course angle, I can find the so-called expression for the cross-track error. Okay. So what am I doing? I'm just simply substituting my chi into this expression for ype. Okay. So we had ype dot is equal to u times chi minus pi p. So if I integrate this, I take a Laplace transform, ype will be u by s times chi minus pi p. That's what you're seeing here. Everybody with me so far?
Yes, sir.
Yes?
Yes, sir.
Okay. All right. So from there, I'm simply substituting the value of chi in here in order to get this value, and whatever is not depending on delta, that terms I'm simply putting all of that together and I'm calling it a disturbance in y. Okay. So now I need a so-called controller which can try to drive my ype to 0. If I drive this thing to 0, it means that I am following the two path. I am following along the line between the two waypoints, isn't it? If the cross-track error is 0, it simply means that I'm going on the straight line from here along this path. Everybody with me so far? So now that we have an expression where ype is related to our rudder angle delta, now we can put a control law on our so-called rudder angle in order to figure out how to suppress that and make sure that ype goes to 0. Yes, no, everybody with me so far?
Yes, sir. No.
Okay, so the primary idea here is that we are looking at the so-called cross-track error to be controlled now by the rudder angle. So we are kind of combined our guidance law where we are giving this so-called desired course angle is what our guidance law was giving us. We are putting that to use in order to get an expression for ype, and now we will formulate a control law of a typical PID type will be sufficient enough in order to drive our cross-track error to 0. So that will ensure that I am tracking the path that I originally chose. So I'm kind of here leaving it here at a point where the next part will be control. So we have gotten our so-called desired heading angle, and we are seeing how that can be used for a control law application. I hope that part is clear for everybody. Yes, no?
Yes, sir.
Yes, okay. All right. Now, typically what happens is this part of the tuning of the gains of your PID controller, you will do for a particular speed u. right? At a particular speed u. And you may want to, you may see some changes in the performance if you tune it for one speed and try to apply it at a different speed. It may not work. So in which case it might be actually better to train to look at different speeds and tune different gain values corresponding to each speed. Okay? So if the speed is time varying in your case, then you can effectively say that our gains also should be time varying to adapt with that change in u. So that is how we typically call, we will try to generally come up with gains which are speed dependent to improve the performance of the system. This part is called gain scheduling. Okay. Which basically is a fancy term for saying that as my operating point is changing, I am having a new set of control gains which I'm going to use for a different set of speeds. Okay, so whenever you see gain scheduling, all that is basically meaning is it is kind of trying to separate out your operating space into multiple regimes, and for each regime it is trying to tune a PID controller's gains. So you have all these gains in hand. When suddenly the situation or the operating point makes a shift, you are actually making a change in the gains in order to use those new gains for tracking and achieving the performance of the control system. More on that when we talk about control. So today's idea was primarily about guidance and how that guidance can be used. Okay, so today we have kind of looked at the idea that how we can relate that course angle which we get. We can relate it to the cross-track error, and which will help us now to relate our cross-track error to the rudder angle, and then we can use the dynamics there in order to tune a PID controller to drive our plant to execute the dynamics which we wanted to execute. Okay. So what we have done today is basically combine guidance with the plant dynamics and leave it at a point where the control actions can now be specified by the controller. I hope that's making sense for everyone. Yes?
Yes, sir.
Oh, fantastic. All right, so now what we will do is, since we have some more time left, we will try to, let me try to talk a little bit about nonlinear stability theory so that we can start discussing about Lyapunov stability and things like that, which will really prove useful when we start discussing about how stable a control mechanism is or how stable a control law is. So let me start sharing that. Okay. So notice that today when we are covering this nonlinear systems or nonlinear stability theory, we will only be discussing the results. We will not be going into proofs and mathematics. Okay, so I'll kind of try to put the result out there and try to talk about intuitively what those results mean. And we'll kind of try to understand from an intuitive sense, from a geometric sense, do we appreciate what he's talking about? But we really will not go into mathematical proofs and other things. So these are all technically theorems which do have mathematical proofs, but we will not be spending our time doing that because the objective here is slightly different. We want to see how these methodologies can be applied for guidance and control of a marine craft rather than spend time on theory and theorems and their proofs. But if you are really interested to look at how these proofs have come up, then you can reference this book by Khalil. It's called Nonlinear Systems. By Khalil. His name is Hassan Khalil. And this is so far one of the most comprehensive textbooks which discusses about Lyapunov theory and what you call how to deal with Lyapunov theory for autonomous and non-autonomous systems. Okay, so with that we'll get started. So this is just a brief review into the world of nonlinear dynamics. There is a much more complex things which are going on. So if you are really interested in this field or if that really excites you, you should look at more complex systems courses. And there's a rich dynamic which goes out in there. We will only be scratching the surface today, but at least that will help us appreciate what we are looking at from the point of view of nonlinear control. Okay, so first thing which we need to bring about is a discussion about what are autonomous systems. So before we can talk about stability and things like that, first we need to discuss what are autonomous systems. An autonomous system is nothing but a vector differential equation. Okay, it's a vector differential equation which is of the form x dot is equal to f of x. Okay, and this form is comfortable for most of you. You have seen this before, especially when you are trying to program things in MATLAB. It expects you to provide it in this format, right? So that same format, the state space representation format, when x here is actually a n cross 1 vector, which means it has n components. But notice here that x dot is equal to f of x. This f also is returning a vector. Okay, this is a vector valued function. But notice how there is no dependence of time anywhere here. I'm purely saying x dot is equal to f of x. X dot is nothing but dx by dt. It is differentiation of x with respect to time. That is equal to f of x. So there is no explicit dependence on time of the derivative of this state space. That system is called an autonomous system. Whereas whenever I have a system which looks like x dot is equal to f of t comma x, where an explicit variation of p is coming into the picture, then such systems are called non-autonomous systems. Everybody with me?
Yes, sir.
Okay.
Yes.
All right. So these systems are called non-autonomous. Now, whenever we are looking at stability, we are usually looking at the idea that there is a initial value problem that I want to solve. I have the differential equation x dot is equal to f of x, where x is a n cross 1 vector and f is mapping from an n cross 1 vector to another n cross 1 vector. And I have an initial condition where x of 0 is given as some x naught. I want to look at how the solutions of this system evolve over time. Right? We want to say something about what is happening to x of t. Now one might wonder, why do I need to really concern myself with stability? I can simply solve the differential equation and see what is happening to it. Why not simply do that? Question is, for a linear system, yes, you can do that. In fact, for a linear system, you need not even do that. Even without simulating, you can specify whether the system will be stable or not. And that can be done in terms of Laplace functions, which we have seen before, right? Laplace transfer function tells us where are the poles of the system, and that will tell me whether the system is stable or not. But for a nonlinear system, a typical nonlinear system, which is given as x dot is equal to f of x, it's not so very easy to figure out whether it is stable or not. Okay, and also the idea might be that even if you try to simulate it from one initial condition and the system does seem to converge to some stable equilibrium point, if you choose a different initial condition, the system may run off. It's possible. So therefore, choosing just one initial condition and figuring out the stability of the entire system is not possible. So there is a requirement in order to govern or to study this properly and come up with the idea that when are such differential equations giving me solutions which are bounded, which are converging, or when are they giving me solutions which are unbounded and running off to infinity. So stability is basically the idea of observing what is happening to these solutions of this differential equation system as I am evolving in time. That's what I want to understand. And many times I want to understand that without actually doing the simulation. I want to have a better approach to understanding stability rather than actually simulating it for so many different initial conditions, which can prove very challenging, especially for nonlinear systems, especially systems which are chaotic and things like that. You cannot try to get this information through simulations. It's very, very hard. So there has to be a different way to take care of that. So that's what we will be looking at primarily when we talk about stability or nonlinear stability theory. Okay, so first things first, we will be dealing with systems where this so-called f of x, okay, is assumed to be a continuous function, which means there is no breaks in f of x, there are no jumps in f of x. At the same time, we also want to impose something more stronger, so we call it as locally Lipschitz, is what is the term which we use. Now, what does that term that f of x is locally Lipschitz in x mean? It means that for each point x that I choose, there exists a small neighborhood of that point such that when I evolve 2 points in that neighborhood forward in time, and I'm looking at what is the value of f, it is bounded by some Lipschitz constants times the norm between them. Now, this mathematical definition may seem a little, complex to understand what is going on, but maybe a better idea might be to wait 1 second. See graphically. So let's see. Let me stop sharing here. Okay. Okay, so what it basically is saying is that yes, the function is continuous, but on top of that, there is a bound. There is I can formulate 2 lines which are looking like these, such that the function always lies to the left or the right of this double cone. It never falls into the white region as that intersection point traverses along the function's line. That's what it means. It's only saying that it is continuous, but at the same time, it is a little well-behaved, a little more stronger condition than being continuous. So intuitively, you can understand that locally Lipschitz means that it is somewhat a stronger condition than continuity, but a somewhat weaker condition than differentiability. Okay, you can kind of intuitively understand it in that sense. The function is continuous, but it need not necessarily be differentiable. So there is a condition in between those two, and that's what I'm referring to as Lipschitz continuity. Don't worry too much about this. This is one of the requirements. So whenever we are looking at such systems, for most practical systems, this will be valid. Okay, our f of x will be a smooth function, so relatively a smooth function. In fact, many times it will even be differentiable. So we may even be looking at a stronger systems than what is Lipschitz. But a Lipschitz is sufficient for our discussion on stability. Is everybody following me?
Yes, sir.
Yes? Okay, good. So let me come back to this one. Okay, so we assume always that our f of x is locally Lipschitz in x, which is a slightly stronger condition than continuity, a slightly weaker condition than differentiability. Okay, and you might wonder why this Lipschitz continuity is needed. This is needed to guarantee that the initial value problem that you have chosen has a unique solution to the initial value problem. In order to prove that, one of the requirements is that this function f of x be Lipschitz continuous. So that is why we are assuming that it is at least Lipschitz continuous. But many times you will find that we can actually go stronger. Most of our systems will be stronger in the sense f of x can be differentiable as well. All right. Now, let xe denote an equilibrium point for this system. X dot is equal to f of x. Okay. This implies f of xe is equal to 0. I want you to take some time and think about this. Is this making sense? If xe is an equilibrium point, why should f of xe be equal to 0?
So the rate of change of x is 0.
Correct. So x is an equilibrium point, which means that if I start at that equilibrium point, I continue to stay at that equilibrium point. That means x dot is 0. It's not changing with time. And if x dot is 0, that means f of xe must be equal to 0. Because the governing differential equation is x dot is equal to f of x. Everybody with me? Okay. So whenever we have such a system, I can equate that f of x is equal to 0 and try to find out what is the equilibrium points of the system. All right. Just so we are able to appreciate this in a slightly better way. Okay. Let's say I have a spring mass damper system. So this is the mass and this is the stiffness. Okay. What is the governing differential equation for this system?
X double dot plus kx equals 0.
Mx double dot
Plus kx equals 0.
plus kx is equal to 0. I don't have any external force right now here, right? So now if I write down velocity is equal to x dot, okay, and I want to express this in terms of a state space format, x and v is my so-called state space vector. Okay, so if I take a derivative of this, that will be given by v, and v dot will be given by minus k by m x. Is that making sense?
Yes, sir.
Yes. So I can write that if I wanted to write this as x dot is equal to f of x, I have succeeded in doing that, right? This is x dot and this is f of x. It only depends on x on v. It doesn't depend on v dot anywhere. Everybody with me so far?
Yes, sir.
Now, if I want to specify, find the equilibrium point of this system, what do I do?
Equate it to 0.
Equate this to 0, right? The right hand side, I equate that to 0. What do I get from that? So basically it's not a scalar value 0, but vector values of 2 zeros. That's what I equate it to. And what do I get from it? What is the equilibrium point?
Zero comma 0.
0, comma 0. So when the position is 0 and the velocity is 0, that is when the system is at equilibrium. Which means if I start at that point, the system continues to be at that point. Any other point that I start, this will not hold true. Is that making sense? Okay.
Yes, sir.
Any other point I start, it will execute simple harmonic motion, as you already know from your vibrations course. Okay, so now coming back to our idea, now we want to talk about this so-called equilibrium point's stability. We want to understand when is this equilibrium point stable or when is this equilibrium point attractive, and things like that is what we want to discuss. So first thing I'll start off with is boundedness. The solutions of x of t are bounded if there exists a non-negative function gamma of x0 such that the norm of this vector is always is less than gamma. So if I can find an upper bound such that for all time t greater than 0, the system does not cross that out. It always stays between that. Then I say that the system is bounded. So if I essentially look at what x versus t looks like, okay, and here I'm kind of considering it to be a scalar, but this equally applies for vector quantities as well. The idea is that you may start off at some point and do all funny businesses, but if I say that I'm confident that you're going to be within these bounds, then the system is bounded. Okay, that's what it means. And notice here that where it is saying that this bound may actually depend on where I initially started. Because I may actually start off sometimes here and then my bound may look slightly different. This might be my new bound, depending on where I start off. So that is possible. Such functions are also still called bounded as long as for any chosen initial condition, I can formulate a function gamma such that gamma of x of 0 provides a bound for the system as it evolves further in time. So you can think of if in your spring mass damper system that if I move it by 1 meter and let it go, I know that the solution will always be less than 2 meters. Right? But if I move it by 5 meters and let it go, I can't say that it will be bounded by 2 meters bound. Okay? At that time, I have to say that now based on my new initial condition, the bound will be 6 meters, let us say. Is that making sense?
Yes, sir.
Krishna Velu, making sense?
Yes, sir.
Yes? Okay. All right. So that is what a boundedness means. Now, the next part comes when this equilibrium point is stable. But unfortunately, it looks like I'm out of time for today. So we will continue again on Monday. Okay. At that time, we will discuss when are an equilibrium point called stable and when is an equilibrium point unstable and how we can determine whether the system is stable or not. Now remember that we are dealing here with nonlinear systems. So we'll not be restricting ourselves in any sense that we are saying and looking at linear systems. Linear systems is something which some of you have already looked at in your different courses. And you know that in such cases, the eigenvalues of the matrix can determine the stability. But we will be evolving more general concepts here, which will be equally applicable to linear and nonlinear systems. So more on that we will discuss on Monday. All right, let me stop sharing now. Are there any questions before I close it down? No questions? Okay, let me stop recording in that case.